This video is going to discuss work, Riemann sums, and how these topics relate to calculus. Work is a concept from physics, and when we discuss work, at least in physics, work is defined to be the product of, the work done on an object is defined to be the product of the force done on the object and the distance the object moves in the direction of the force. So in a basic sense, we can actually write work as force times distance if, and here's the key assumption, that if the force is constant. Okay, so if the force doesn't vary, it's you push a box with the same amount of, or you apply a force on an object the same amount over the entire distance it travels, then we can just express it as force times distance. Now again, we're assuming there's more to this topic of study. For example, we're assuming right now that the force and the distance are applied in the same direction. If they are not, for example, if they're applied at a 90-degree angle, then there's going to be this is actually going to be called the cross product instead of a multiplication. And then there's other mathematics involved there. Okay, but for right now, we're assuming that the work is equal to force times distance, and at least for this module, force and distance are applied in the same direction. Okay, now force may not always be constant, and so that's where the other scenario comes into play. Okay, and this is, so if a force isn't constant, it is variable. So think of pushing it up the hill. You're probably going to have to apply more force to get it up the hill as the hill may become steeper and steeper. Okay, so the force is going to depend on the distance it's traveled already. So depending on where it is, you may have to apply more or less force. So the mathematical way we can represent this is using that same idea that force, or that work is force times distance. We can determine the force over some distance, and then that force is going to be multiplied by the change in the distance. Okay, and then for the next segment of next distance that you travel, perhaps it requires a little bit more force, so you have to determine the force for that period of time, that distance, and then determine how far that distance was, or how far that force was applied over. That's delta d2. Okay, so if I'm writing this out, this is the force, and then this is the distance the force was applied. Okay, and D1, just note that this is actually evaluating. So a note here, this is evaluating force at D1. Okay, so if we're going to actually do the calculations with all this stuff, so it'll make more sense once we get to the numbers, but just at least at a basic level, this is what the notation means. So we have to add up all these different chunks of distances to get the entire distance, right? And so we may have, say, n different intervals that we have force being applied over. So in shorthand notation, we can use a Riemann, or a sum, a sigma notation. So this is starting sum at 1, going to n, and adding those products together. Okay. Now a diagram of just what we may be experiencing. So if I have, let's say, here's my function for force. Okay, and I'm concerned with starting at, I'm going to call this 2, and I'm going to go to 10. Okay, so let's say, and this is my variable force. Okay, and I'm going to use capital F. Okay, here's my distance. This is D. Okay, and I need to break this up into intervals. So since it is variable, it's not constant. Perhaps I'm going to do something like this. And so really when I take those products, I'm multiplying the force value times the distance that it's covering. So really what I'm doing each time is I'm making rectangles. So, and then the next one, I'd go up to the curve. This would be the force value. Okay, so now I'm at force part 2. And then this delta D2 is represented by this period. So this would be delta D2. And then I can compute that, so I get another rectangle. And then I have force D3, so that's up here. And it goes for delta D3, goes over. So that force we think of as constant. And so what I'm getting is I'm getting a pretty decent approximation for work. We'll actually talk about how to find this exactly in a different video. But at least in a rough sense, what we're going to be doing is finding essentially the area under the curve via rectangles. Okay, so using this idea of work, here's an example that we can start to dig our teeth into. So an object moving straight line motion, interaction variable force, blah, blah, blah. I'll let you read it on your own. And so we're given this function and we're looking over the time period 0 to 3 meters. So 0 to 3. And now here, I didn't give us the number of approximating rectangles. I didn't give us any further information. But the idea is, okay, I know the graph of this. It's a parabola, and so it's going to start up 1 unit and then slowly increase something. Maybe I'll make it a little less drastic, just so it fits in the space that I have. So it's going to go up like this. So here's 1, and then here's the end point. So again, it's going to look something like this. And what we need to do is estimate the work done. So again, this would be the force. My entire distance is here, but the force is not constant, right? So I need to break this up into intervals. And just for easiness with computing, I'm going to go by units of 1/2. Just to make the computation easier. In reality, you'd probably do more. Okay, so I have different intervals here. You can use more intervals, less intervals. The more intervals you use, probably you're going to obtain a better answer. But so the idea, again, just as we saw in the last slide, was we're going to try to make rectangles here using a left endpoint. So find the function, or find the force at 0 multiplied by the distance, so I'm going to call this delta D, distance here, I'm sorry, that's delta D. So that would give me the work from 0 to 0.5. Repeat that process here. So evaluate the force at 0.5 multiplied by delta D. And so again, I'm taking these rectangles piece by piece to estimate the work done on the object, okay, since the force is variable. Okay, now I'm going to save myself some time. You can do this with a calculator, but essentially what the calculation is going to boil down to is you can make a table, and we'll fill this out soon, but what we're going to do is work is going to be the force at 0 times delta D, and we'll get to that in just a minute, plus force at 0.5 times the change in the distance, or the distance over which that applies, plus the force at 1 times delta D, plus so on and so forth. And the last rectangle that we're going to get would be evaluating at 2.5, so plus f of 2.5 times delta D. Now delta D here, I split it up into nice intervals. You can split it up however you would like, since there isn't any information in the prompt, but delta D here was 0.5, and that was just by my own picking. Okay, so let's do this in Excel quickly. So D, these are the points at which I'm going to evaluate the force. So these are going up by 0.5s each time. 1, 1.5, 2, 2.5. Okay, and then to get the force, I'm going to cell reference the distance, square it, and add 1 according to the function, and then carry that through to the rest. Okay, so now I have the force. I need to compute the change in distance. This was actually constant. Oops, 0.5. So I'm going to just drag that down. Now, to compute the work, again, I would have to compute, and I'm just going to start this, the force times the distance, okay, so, or the change in distance, okay, and I can drag that down, and then so my total is just going to be the sum of the force times the change in distance, okay. Okay, and there was some error in Excel when I did this quickly, but it should end up being about 9.875. And another way you can do it is you can use the command sum product, and then you don't have to compute these, but you can just select the forces and the change in distance. And what this does is it multiplies, it takes this cell times this cell and adds and continues those products and adds them all together, and you should get the same thing. Yep. So we're going to say that the force here is 9.875, and using the units, I believe it ends up being newtons. Okay. So this through Excel, or you can do this by hand too. This is about 9.875 newtons. Okay, since it is in meters, and right. Okay. So what all this is alluding to is Riemann sums. Okay, so everything that we did was a Riemann sum, which essentially is a fancy way of saying a sum of rectangles underneath the curve at a specified endpoint. So again, we saw the picture, but again, just to reiterate, if we have a function, something like this, and we're starting at A and ending at B, then I can compute, and then we're only going to consider the left-hand Riemann sum, but I can actually make approximating rectangles here. Okay, and sometimes they're going to be accurate, sometimes they're going to be over, sometimes they're going to be under, but every time I make these rectangles, I'm going to take or make it so that the left endpoint hits the function, and the right point, or the right endpoint, would just be straight, so I get an actual rectangle. Okay, and assume that I drew this all correctly. But essentially, what a Riemann sum is, I draw these rectangles such that the left endpoint hits the curve and make it into a rectangle, and then add up all these areas. Okay, and just a bit of notation, we use L of n, L sub n, to denote the left Riemann sum. There are right-hand Riemann sums and midpoint Riemann sums. Those are for another extension, if you wish to learn a little bit more about this topic. Then the last thing that I'll mention is we can use that force equation that we developed back on this slide, where we did force at the endpoint times the distance that it was applied over, and that actually extends directly into a Riemann sum, or actually work is actually a consequence of this Riemann sum, but I digress. And so all this is saying is that the left hand Riemann sum, we take the change in distance, so the interval width, okay, so each of these is delta x, okay, delta x. So that would be the width of the rectangle times the height of the rectangle. So this is width, and this is height. Okay, so I'm just doing a little geometry, find up all the areas, add all the areas together. Okay. Also, one thing that I want to point out is if we're ever asked to find the interval width, so we have the two endpoints and we're splitting it into some number. This is number of intervals. We can compute delta x by that. Okay? And that's a brief look at left-hand Riemann sums and how they apply to work.